Monsieur Raouf, on cède la parole à Monsieur Raouf pour démarrer la première conférence.
J'espère que c'est possible, n'est-ce pas? Je passe en français. Je pourrais essayer, mais je veux vous éviter l'expérience de faire en français, donc je ferai ça en anglais. J'en ai besoin vraiment. Vous m'entendez bien? Mieux avec ça? Bon, ok. On va utiliser ça alors. Je disais que c'était toujours un grand plaisir pour moi de venir en Tunisie et je remercie donc les organisateurs de m'avoir invité. Donc j'ai présenté. Okay, let's switch to English. So my talk is in the area of cloud resource management, and this is an area that I work wise. And so today I'm going to tell you about some of the research challenges in this area, and which are also opportunities for research. I'm going to focus my presentation, since it's only 1 hour, right? So on one particular challenge, which is the, in my opinion, largely overlooked in the research literature, which is the heterogeneity of cloud environments, heterogeneity in terms of the cloud resources, the infrastructure, as well as the workload submitted to the infrastructure. And this is largely overlooked in the research literature, meaning that most of the research papers you see in the literature are hardly applicable in practice, or at least if you implement them in practice in the real world, they will result in suboptimal performance. Okay? So I have to go back here. So how does it work, this one? All right, so this is the outline of my talk. So I start with a brief introduction to cloud computing. I know it's a school. I hope that you still have some background in cloud computing. My introduction will be very brief. Anyway, anytime if you have any questions about the background, feel free to interrupt, okay? Just raise your hand, ask questions. I'll be happy to answer that. So again, I will try to explain what I mean by the heterogeneity challenge, and in order to illustrate this, I'm going to use real data traces from Google backend cluster, one of the biggest clusters of Google, as well as other data from other major players such as Yahoo, Facebook, and Microsoft. Okay? Once we understand the heterogeneity challenge, I'm going to pose a number of questions stemming from there, and then show you, depending how time permits, a couple of research projects undergoing Waterloo in my research group addressing these challenges. And hopefully I'll conclude after that. How's the pace? We can do flow control. If I'm speaking too fast or too slow, let me know, right? Anyway, so in recent years, we have witnessed the rise of cloud computing. Actually, we didn't only witness it, we contribute to it, right? The rise of what I call internet-scale applications, very large-scale applications, and these applications can be personal applications such as Dropbox or iCloud, social networking applications such as Facebook, Twitter, LinkedIn, video applications such as YouTube, Netflix, and others. And what characterizes these applications is that they are very, very large scale. They reach to a very large number of internet users, and they are very resource intensive. They need massive amounts of resources in order to operate, and they can also have stringent performance requirements. For example, response time for most of them, okay? All right, so since they are very resource intensive, the providers of such application typically deploy massive infrastructures. Take an example, large-scale infrastructures, Google. Google is the largest cloud provider in the world today, has over 200 clusters deployed all around the world, hundreds of thousands of machines, okay, to provide cloud, for example, the Google search engine and all kinds of platforms that Google provides and services. And these typically infrastructure are also known to basically manipulate huge volumes of data. Just to give you again an example, look at Facebook. 36 petabytes of stored data, processing 80 to 90 terabytes of data per day. And these statistics date back to 2010. You imagine that these numbers are much higher today, especially with the advent of 3D photos, which are much more memory greedy. Okay, so the numbers are really skyrocketing. Okay, so what is exactly cloud computing? So from one perspective, it's new, but it's not that of a new concept, okay? It bears many similarities with other distributed computing models, such as grid computing, high-performance computing, cluster computing, to name a few, but it has also some unique characteristics. Maybe it's closer to the so-called utility computing that appeared a few years before, but didn't make it really. I think what made cloud computing successful is the underlying business model. Okay, this use as you go and pay as you go type of economic model. It also has, from a technological standpoint, one particular characteristics that kind of differentiate it compared to previous model, which is the extensive use of virtualization technology, okay? So anyway, you can think of cloud computing as a distributed computing model that is designed for running these large-scale applications in a cost-effective manner and in a way that basically realizes the service level agreements or whatever quality of service expected by these applications, okay? So how is this done? Basically by harnessing massive resource capacities. Why is not with this one? It's not working anymore. Okay. Yeah, here we go. So harnessing massive resource capacities in the so-called data centers, okay? Do you know what a data center is? Anybody saw a data center? No? Okay. You can think of it as a very large space, typically in remote areas where the cost of the land is cheap, okay? And you have many, many rooms containing many, many racks of server blades and disks and computing devices interconnecting these, and of course, air conditioning and cooling and power next to a significant energy source and whatnot. So basically, a lot of these machines there deployed in data centers, and these machines and resources are shared by the applications, okay, in an on-demand basis, also with the possibility to scale up and down dynamically. So basically, resources are allocated to application, but if the application needs more resources, it can scale up and down instantly, okay? And that's an interesting, what the so-called elasticity, and an interesting feature of cloud computing environment. So roughly speaking, the players involved in a cloud computing environment are three. There are the so-called cloud providers. I think this one is not really working, so let me just get rid of it. So cloud providers, also known as cloud infrastructure provider, they own the infrastructure. They own the data centers and whatever and the servers, and they lease these resources to service providers, okay? And the service providers rent the resources from the infrastructure providers in order to deploy application and services and make them available to end users, okay? These are the three main players in a cloud computing environment. All right, so what makes cloud computing successful are, of course, the benefits that it brings, and among them, the first and foremost is economical benefit, and because cloud providers leverage cheap commodity hardware. Basically, instead of relying on expensive, say, high computing hardware, they buy basically a large number of cheap commodity hardware, replaceable hardware. It fails, it's okay. Just replace it with another one. And leveraging also the economies of scale. By buying a very large number of such machines, they bring the unit cost of these machines down, okay? Another advantage is it's highly scalable. So from the end user perspective, the cloud computing provides the illusion of infinite resources on demand, okay? You can get as many resources as you can pay for, right? And from the small and medium enterprise perspective, and these are nowadays considering to outsource their IT infrastructure to cloud providers, but the benefit is that they can avoid the upfront investment cost in the IT infrastructure. They can basically start small and increase the resources based on the success of their products or services, right? So they can scale up and down flexibly. In terms of flexibility offered also by cloud computing is the fact that you can customize CPU, memory, storage, and networking capabilities. For example, you can say, I want a virtual machine with that number of cores and that much memory and whatnot. And you can also customize the software stack as well as the protocol stack, network protocol stack. You can say, I want this operating system, this version of the operating system, and whatnot. And finally, easy access is another benefit of cloud computing, that you can access the resources deployed in the cloud from anywhere where you have an internet connection. You can access the application running in the cloud, or you can deploy applications in the cloud on the resources that you lease from anywhere also, provided you have internet access. Okay, so as I said, I'm going to focus my talk on resource management because this is the area I'm interested in. And resource management, as you can imagine, is a very important topic here because of the scale of the problem. It's a central activity in cloud computing environment. And we look at resource management from two perspectives: the perspective of the service provider and the perspective of the cloud provider. And these are the two of the major players involved in this type of environment. So from the service provider perspective, resource management is mostly concerned with basically providing services to end users while guaranteeing the performance expected by the end user applications in a way that hopefully minimizes the rental cost of the resources from the infrastructure provider. Now, from the infrastructure provider perspective, resource management involves a number of traditional management activities, such as capacity provisioning enough capacity to support the service providers and users, monitoring the usage of the infrastructure and the workload, scheduling and allocating resources to service providers and applications, detecting problems when they occur and handling these problems. These are all traditional management activities, but there are also less traditional management activities, and one of them is energy management. And energy management is very important for various reasons. One of them is the fact that it costs a significant portion of the operational expenditures of an infrastructure provider. Okay? And I'll come back to that a little bit later. How's it going so far? Okay? All right, so I mentioned the heterogeneity challenge, and as I said, cloud resource management is a very difficult problem because of the scale or the magnitude of the problem, but also because another reason that has been largely ignored in the recent literature, which is the heterogeneity, and the heterogeneity of the infrastructure itself, as well as the heterogeneity of the workload executed on the infrastructure. So machines in cloud environments have heterogeneous processing capacities and capabilities. For example, different processor architectures, different hardware features, different processor speed, memory size, and energy consumption models. Okay, and the workload or the application executed in the cloud also are heterogeneous in terms of their sizes, the duration, execution time, the priorities of these applications, and their performance objectives. Some applications are more sensitive to, for example, completion time, others to response time, and whatnot. Okay, so there is an inherent heterogeneity of both machines as well as application, and this has not been really taken into consideration in most recent work, and failing to do so will obviously result in suboptimal performance in many of the resource management activities, for example, in scheduling tasks for execution in the cluster. Okay, I'll explain why we have this heterogeneity in the first place later on. Okay, let me take a Google case study just to make things a little bit more more practical. Okay, so we have a project with Google, a major project funded by Google, and as I mentioned before, Google has the largest cloud infrastructure in the world, and each of these clusters at Google executes millions of tasks on a daily basis. Okay, and so Google obviously maintaining its infrastructure from time to time wants to implement all kinds of management activities, for example, to change the scheduler, upgrade the scheduler to a new version, or for example, upgrade the capacity of its clusters to, in response to, for example, to the evolution of workloads and whatnot. And basically one very important thing for Google in order to, before implementing such maintenance or management activities, is to evaluate the impact of these management activities before implementing them in its clusters, okay? And the way Google does that today is by resorting to simulations, okay? Very large-scale simulations using historical data traces. And this exercise turned out to be very expensive, very high overhead exercise, because just for one reason, Google has an entire group based in Seattle that is dedicated just to building and maintaining the simulator. All right, so it's a quite sophisticated simulator, and also another problem that Google has, besides the fact that this is an expensive process, is the fact that the simulation generates all kinds of results. Most of them are difficult to analyze. Okay, and finally, it is difficult using simulation for Google to analyze what-if questions, because it relies on simulation based on historical data traces, and they cannot simply project themselves into a situation that is not supported by the data traces or historical data traces they have. So from Google point of view, understanding the characteristics of the infrastructure and the characteristics of the workload they have is very important. For one thing, to simplify the analysis and hence reduce the overhead, as well as also providing the ability to develop better scheduling and resource management techniques or mechanisms or algorithms that better fit the environment they have. Okay? So that is the main questions that faced by a major provider or cloud provider such as Google. Okay, so now I mentioned this heterogeneity. Now let me show you what this exactly means by looking at one particular cluster, one back-end cluster at Google, one significant one. So we have access to this the data traces through this collaboration project with Google. Okay, and so basically we analyzed the data to understand the magnitude of this heterogeneity I mentioned before. Okay, so this is a little bit about the data traces, the Google data set we used. So the traces were collected from a production compute cluster in Google over a period of 29 days and involve over 12,000 machines, executing over 2 million jobs and 25 million tasks, okay? So applications are represented by jobs in Google Lingua, okay? And each job consists of one or multiple tasks. So Google also uses priorities, or jobs and tasks have priorities, and basically when a high priority job arrives, eventually it can preempt a low priority one, and actually uses, to be precise, 12 priorities that are divided into 3 priority groups, okay? The so-called gratis priority group includes priorities from 0 to 1, and these are low priority batch jobs, for example, map-reduced jobs, jobs that are, for example, analyzing logs, the other priority group includes priorities from 2 to 8. Okay, and these are medium priority tasks, such as monitoring the infrastructure type of tasks. And then production priority group, these are the highest priorities, includes priority 9 and to 11. And typically these are the user-facing applications. So user-facing applications are typically web services, okay, web services that have, for example, stringent requirements in terms of response time. Okay, for example, Google wants, for example, to resolve any search query within half a second, okay? So these are typical search, for example, web service to provide search or other type of web services, okay? So we looked at this particular data set, and this is what we found. We found that there are 10 types of machines. I'm gonna go back here. So we have 10 types of machines, as you can see here. The machines are differentiated in terms of their normalized CPU and memory size, and these are the number of each type of machines. Okay, so and so basically this tell us that machines in typical, you know, in practice in clusters are of different types. Okay, there is a clear heterogeneity in terms of the types of machines deployed in clusters. And why the reason? The main reason for that is that machines are deployed over time. For example, first of all, we can buy different types of machines because we want to support different types of workloads. Okay, for example, for some workload we need higher capacity machines. But then also machines are also purchased over time. For example, one machine fails, is replaced by another one, a newer one, have higher capacity or different type of processor architecture and speed and whatnot. So at the end of the day, we have a cluster that is made of machines of different types and heterogeneous. Okay. We also look at machine availability. That's the second figure over there. Machine availability over time. Okay, and we found that machine failures are common in cluster in cloud computing environments, basically confirming that these machines are, you know, cheap commodity hardware that typically can fail from time to time. And we see that we have quite a significant fluctuation in machine availability over the 29 period. Time period, okay? Now, one thing that we cannot say for sure is that these machines have indeed failed, okay? They can be also turned off and taken for routine maintenance purposes, okay? But some of them clearly must have failed. Okay. So we looked at the application heterogeneity, okay, in terms of job priority and job sizes. And we found that most of the jobs have low priority. As you can see, the majority of jobs here belong to the gratis and other priority groups. And about 7% of all jobs executed in this cluster are production jobs, high priority jobs, all right? And we also looked at the job sizes in terms of number of tasks in these jobs. And we found that most of the jobs are small and some of the jobs are very, very large, okay? So we can see here that about 50% of the jobs have 10 tasks or less. And some of the jobs, few jobs, can have several orders of magnitude more number of tasks, okay? Thousands of tasks. We also look at the task sizes, and task sizes in terms of their CPU and memory requirements. And we looked at that for all three priority groups, gratis, other, and production. And what we have found here, as you can see, is that most of the tasks are small, okay? This is the CPU size, or CPU requirement of tasks, and this is the memory requirement of tasks. And you can see that most of the tasks are small in terms of their CPU and memory requirement. But some tasks can also be very, very large in terms of their CPU or memory requirements. Okay, so here the circles, or the radius of the circle, is logarithmic in the number of tasks in its proximity. All right, so you can see that for all three priority groups, most of the tasks are small, but some tasks are either have high requirements in terms of CPU or high requirements in terms of memory. Maybe one exception with the production priority group, where the large tasks much larger than the smaller tasks, are more CPU intensive than memory intensive. So we also looked at the task duration and the scheduling delays. The task duration is the time it takes a task to complete. And what we found is that most of the tasks are short, okay, less than 10 minutes, as you can see. About 50% of the tasks finish within 10 minutes or less, but some of the tasks can take several days to complete. One exception is the production, that's the green line, the production type of tasks that take several days to complete, sometimes 29 days, as we can see here, okay, which makes sense. Web services are deployed for, you know, for the entire, for longer periods of time, all right? And we look at the task scheduling delay. And the task scheduling delay is the amount of time a task waits when it arrives to the cluster until it is executed in the cluster, schedule it for execution in the cluster. And here again, we find that more than 30% of the tasks for the gratis and other group, and 50% of the priority, the high priority production priority group, are executed immediately or scheduled for execution immediately. However, we found also that some tasks can wait for long periods of time. Actually, we found even that some production tasks can wait for 21 days, okay, before they are executed. And our speculation here is that either these tasks have unreasonable requirements in terms of resources or have very difficult requirements to satisfy in the cluster. And that's intriguing because looking at the availability of the cluster over time, the cluster is not all the time 100% busy. Okay, which means that basically there is a margin to improve the scheduling, okay, in such a way at least to better accommodate these hard to schedule tasks in the cluster than it is the case today. Obviously, understanding the characteristics of the tasks and the workload and understanding the characteristics of the cluster will allow us to do a better job in scheduling resources and allocating resources to application in the cluster. Okay. So the other data traces we looked at are MapReduce data sets. You're familiar with MapReduce? Who's familiar with MapReduce? Raise your hand. 1, 2. All right. So that's it's fine. I have a couple of slides to explain what MapReduce is. So it's very important. This is one of the most important type of applications that are executed in cloud computing, cloud environments today. Okay, so it's a computational model, more leveraging parallel processing in order to execute large batch jobs. Large batch jobs are jobs that basically process very large amounts of data. Okay, and very, very significant amount of the workload executed in cloud computing today is based on this computational model. Okay, so the idea is basically given an amount of work, okay, to be done, okay, for example, analyzing or mining a very large amount of data, okay, then divide this amount of work into pieces, all right, assigning these pieces to different workers and dependent workers that can work in parallel and process these pieces of data, generate intermediate results, okay, that are then combined to basically come up with the final output of the job execution. So there are two main phases in here. There is a partition phase where you partition the original data into pieces, and there is a combined phase where you combine the intermediate results to generate the final output, okay? So this is the main idea. So divide and conquer in order to process very large amounts of data, okay? And to implement this concept, MapReduce is the most prevalent model, computing model in cloud environments today, okay? So it was invented by Google. It basically inspired from functional programming where you have the map and reduce tasks. So you can think of the map task as the partition phase and the reduce task is the combine phase, hence the name MapReduce, okay? So let me give you an example, all right? So in this, let's say, for example, we want to count the number of words in a very, very large file, data file, all right? So of course, we're talking about eventually terabytes of data that you need to process or mine or whatnot, or implement whatever machine learning type of algorithms on it, okay? Make the data speak. All right, so say in this file, we want to count the number of occurrences of each word. So this is the original file. We're going to divide this original file into, say, 2 lines of text, okay? And each 2 lines of text are assigned to a different map task, okay? These map tasks, okay, are independent, can work in parallel, and count the number of occurrences of words in each of these 2 lines of text, all right? And as you can see, the first map is assigned these 2 lines. I'm going to find that there is 1 occurrence of the word the, 1 occurrence of the word brown, fox, and quick, okay? And then we have another phase, which is the reduce phase. And here again, we can have more than 1 reducer, multiple reducer. Each reducer is assigned a number of keys, okay? Or is responsible for some of the keywords. For example, the first reducer is responsible for the words brown, fox, how, now, and thee, collects the results of the map tasks, okay? And then combine these results. The reducers can also work in parallel and independently, and together will generate the final output, that is here the number of occurrences of each and every word in this input data file. Is it clear? Okay, so that's MapReduce. Now, there are multiple implementations of this MapReduce, or this computing model. There is DRIDE, for example, used by Microsoft, but the most popular one is known as Hadoop. Hadoop is an open source Apache project that is basically initiated by Yahoo, and it is used by most major players in cloud computing environment, okay? So Hadoop is used basically to implement this model for batch processing, all right? So we look at data, for example, in a Hadoop cluster at Facebook, all right? And we found that about 55% of the jobs, MapReduce jobs, have 2 map tasks or less. And then if you look at the, say, if you look, for example, at the top, say, 1% larger jobs, they're composed of several thousands of map tasks. So at least 2 orders of magnitude larger than the small jobs. So the majority of jobs are small, but there are few jobs that are orders of magnitude bigger. And this result is confirmed by another study done by folks at Berkeley in the US. They analyzed the data of another cloud provider. The name is withheld, so it's called Internet Company. So for some reason, the name was not disclosed. And you can see that here again, we see that about 50% of the jobs have 10 map and reduce tasks or less. But we see that 5% of the jobs can have several thousands of map and reduce tasks. All right? So we looked also at the distribution of job length. Okay, and as you can see, it's quite uneven. We find, for example, the job length in terms of execution time. And we find that 50% of the jobs in a Hadoop cluster at Facebook finish within 90 seconds. Okay, but looking at the 1% larger duration jobs, they finish within 5,000 seconds. This is an hour and a half. All right? And the same thing was observed at the Internet Company by the Berkeley folks. So we can see that about 50% of the jobs finish within 80 seconds, and the 10% larger jobs finish within about more than 10 minutes. And same thing in a research cluster at Microsoft. We can see that 50% of the jobs finish within 30 minutes, and then about 5% of the jobs, the larger ones, finish within 5 hours. So we can see here that there is an uneven distribution of job length, okay? So look also at the sizes of tasks, of MapReduce tasks in terms of their CPU and memory requirements. And we find that the majority of the tasks, again, are small in terms of the CPU and memory requirement, but some tasks have very large CPU requirements and others can have very large memory requirements. So you can see here the map tasks are the purple circles and the reduced tasks are the pink circles. So we can see that, for example, the map tasks are more CPU intensive and the reduced tasks are more memory intensive. Okay? Okay, we also looked at the arrival rate of jobs, okay, and actually it's quite obvious. It follows an on-off pattern based on the time of the day, whereas during daytime the arrival rate is very high, around 40% job enter arrival time is less than 10 seconds. However, at night time is the opposite situation, and the job arrival intervals can be very, very long. Okay. Now, combining what we've seen in the previous slide, the uneven distribution of job length, and this observation about the arrival rate, we can basically conclude that the arrival rate of slot requests, and slot is the unit of machine that is allocated to jobs, you can think of it as a virtual machine, can be very spiky. Okay. Now, acknowledging this heterogeneity, we can ask a number of research questions. There are many of them. I'm going to just cite a couple of 2 or 3 here. One of them is the lack of performance model that captures the heterogeneity of the infrastructure and the heterogeneity of the workload. For example, what performance metric should we consider in this case? Should we consider queuing delay or scheduling delay, the preemption rate, the completion time? What are the most important metric that capture the heterogeneities, and how to evaluate these metrics is an open research question. There is no such performance model out there. And also, what is the impact of the scheduling on these metrics? Okay, talking about scheduling, how to design scheduling algorithms that capture also the heterogeneity of the workload and the heterogeneity of the machine characteristics. Are there good bin packing algorithms that, for example, take into account the distribution of task sizes, as we have seen in the data traces? So obviously, jobs have different requirements. For example, if you look at MapReduce jobs, they're more sensitive to completion time. If you look at user-facing jobs, they're more sensitive to response time. You cannot use the same scheduling policy for these different types of jobs. So you need different scheduling policies. Or how to avoid frequent preemption of long-running tasks. Using priorities, for example, during spiky or busy hours, long-running tasks would be preempted repeatedly. And this will lead, for example, to resource wastage and eventually prolonged execution time for these tasks. So there are a number of questions also pertaining to how can we do good scheduling given the heterogeneous characteristics of workloads and machines. I mentioned energy management as a newer research problem in this context, and how to leverage machine heterogeneity and job arrival pattern to save energy. Typically, energy saving or energy consumption is typically reduced through the so-called server consolidation by turning off the machines that are unused in the cluster. And if you want to do that, you have to know what type of machines you need to turn off, all right, or turn on, actually, to provision the cloud in a way that supports the workload. Okay, so these are interesting questions taking into account heterogeneity here. And finally, optimizing workload performance and resource efficiency using migration. So here, virtualization is used extensively in these environments, and virtual machines, for example, are deployed as a way to allocate resources to applications. And virtual machine migration is a mature technology today that is used extensively for various management purposes. For example, to route around a network hotspot in the data center, all right? Or for example, to reduce resource fragmentation, where you have many servers that have, or the workload is fragmented over a very large number of servers. Or for example, to minimize energy consumption, as I mentioned, by packing as many virtual machines as possible on a fewer number of servers, so you can offload completely some other servers and turn them off, and thereby saving energy. And so how to use migration effectively, okay, given the heterogeneity of machines as well as workload, is also an open question. Any questions from you so far? Okay. So let me then show you a couple of examples of research projects in my research team that try to address some of the questions that I just announced. One of them is about preemptive scheduling for MapReduce jobs, okay? I mentioned that we've seen in the traces that resources are occupied by low priority jobs most of the time because it is the largest number of jobs in the cluster. Now, we have seen also that slot requests can be very spiky, okay? And during busy hours, what's gonna happen is that we have both production and non-production job that arrive in the same time. And when this happens, high priority jobs, production jobs, are allocated higher shares of resources for obvious reasons. They have higher priority. So what is the problem with that? The problem with that is when large jobs arrive, basically they can cause many tasks to be preempted, lower priority tasks to be preempted. Now, if these tasks are long-running tasks and can be preempted repeatedly, this will result in resource wastage, okay? Because all the time that the resource task has been executing and using resources, after it is preempted, all these resources would have been wasted, all right? In addition to that, these tasks, okay, it can also result in prolonged execution time for these tasks. So the problem is quite obvious, okay? And the solution can also be very obvious. So so basically we have a very simple solution to that. We call global preemption. And the idea here is to the main idea is to trade short-term fairness for higher throughput. Let me explain. So first of all, looking at Hadoop. Hadoop, the de facto standard MapReduce tool that exists out there. Its current version is called Hadoop Fair Scheduler. And Hadoop Fair Scheduler, what it does, basically, as the name indicates, it tries to achieve fairness. So when it comes to preempting tasks, what it's going to do, it's going to preempt tasks over all jobs in a proportional manner for fairness purposes, okay? So our idea is to change that a little bit and to trade off short-term fairness for throughput. How are we going to do that? Basically by separating long-running tasks from short-running tasks, long tasks from short tasks. And we have seen that we have a clear pattern when we looked at the data, okay, in terms of tasks that are very short, the majority, and there are few tasks that are very, very long, orders of magnitude longer than these ones, okay? So the idea is to classify tasks into short tasks and long tasks. And then having done that, what we do is when it comes to preemption, is to preempt short tasks first, as opposed to long tasks. So very, very simple idea. Okay, so this is how we do it. As I mentioned, we profile to identify long tasks using clustering algorithms, and here you can use very simple clustering algorithms such as the k-means that allows you basically to cluster tasks into small and long tasks, and then keep track of the allocation of resources to the long tasks. So basically we create a virtual pool of resources that is dedicated to long tasks. And the main purpose of this virtual pool is to protect these long tasks from preemption, okay? Now, so this is the main idea. Then the challenge is, how big is this virtual pool of resources? How much resources we're going to assign to this virtual pool dedicated to long tasks? And obviously this has to change over time depending on the workload situation and the resource usage in the cluster. So the challenge is to find this in a dynamic manner, or to tune the size of the virtual pool in a dynamic manner. And the algorithm is shown here. I'm going to spare you the details, but the main idea is, if there's a lot of resources available in the cluster, we increase the size of the virtual pool, and during busy hours when the resources are more are rare, then basically we decrease the size of the virtual cluster. And the reason we do that is because we don't also want to starve short tasks. Okay, the more we allocate resources to long tasks, the more basically we take from the short task, and eventually leading to starvation for such tasks. So we try to avoid that in the same time. Okay, let me tell you about the experiment. So again, the idea is extremely simple. The problem is there for sure. The idea is extremely simple, so we try to experiment with it and see whether it can improve really the performance. So we deployed this in a cluster actually composed of 101 large Linux instances on Amazon EC2. So basically we rented from Amazon EC2. Each instance has 15 gigabytes of EBS and 850 gigabytes of local storage. These are details about the the experiments. And for the workload that we used a mixture of workloads consisting of grep, aggregate, and sort. These are typical applications for which MapReduce can be very useful, or MapReduce is used for these applications. And we use two types of workloads: IO-intensive workload, or workload that basically read and write in the disk very often, as well as mixed workload. And mixed workload is composed of both IO-intensive and CPU-intensive workload. Okay? And then we implemented GP, this global preemption policy, very simple policy, by modifying Hadoop, all right? And then we also ran and compare with Hadoop Fair Scheduler, which is the de facto, well, the state-of-the-art Hadoop implementation today, okay? So the performance metrics we used to compare, to evaluate and compare these two are the following: the average response time, which is the average running time of jobs; the application normalized performance, which is the ratio of ideal running time over the actual running time; the system normalized performance, which is the geometric mean of all ANPs; the unfairness, which is the coefficient of variation of the application normalized performance; and the slowdown norm 1 and 2, which are basically the slowdown in terms of job execution in the case where GP is used compared to the ideal case where, for example, job get all the resources it needs, okay? And that's the what we found. Again, I just give you a snapshot of the overall technique and results. And so we have the system normalized performance here. So we have the current Hadoop with IO-intensive workload, that's the black bar. And then we have the current Hadoop with the mixed workload. This is the third bar, okay, the gray one. And then we have GP, our scheduling policy with IO-intensive workload, the second bar. And then the white bar is GP, our policy with mixed workload, which is the fourth bar, okay? So here we see the system normalized performance in the first figure. The x-axis is the percentage of jobs running in the system when we inject long-running tasks. So P equals 0% means we inject the long tasks immediately, and 50% means after we inject the long-running tasks or the long tasks when after 50% of the background jobs are already executing the cluster, and so on and so forth. So what we see that basically GP, the second and the fourth bar, outperform the Hadoop Fair Scheduler in terms of system normalized performance, okay? Which makes sense. What's more basically, what is quite counterintuitive is the fact that GP, as we can see in the second picture here, outperforms Hadoop Fair Scheduler even in terms of fairness, okay? So we can see that the unfairness of the coefficient of variation of the ANPs, which is the mean over the standard deviation, as you can see, is better with GP compared to Hadoop Fair Scheduler. And the explanation for that is the fact that because we preempt less these long-running tasks, then we have more consistent execution time even for these long-running tasks, which are typically get preempted repeatedly during busy hours, okay? Then we see the average response time, and we see again that GP outperforms the Hadoop Fair Scheduler, and the slowdown norm 1 and 2 confirm these results. These are the bottom pictures. All right. Let me show you another instance of research project that we did basically to deal with the issue of energy management, all right? And through, and we addressed that through a dynamic capacity provisioning. So we call this system Harmony for dynamic heterogeneity aware resource provisioning in the cloud. So first of all, why energy? Why dealing with energy cost? Because as I mentioned before, energy cost is very important. Actually, according to data from Gartner, it accounts for 12% of data center operational costs. 12%, okay? And this dates back to 2010. Now we're talking about even more, all right? We're talking about millions of dollars that goes into energy cost. Energy cost, why? To power on all these servers and machines. We're talking about thousands of servers that you need electricity to power them on, all right? And you need also electricity for the cooling okay, to maintain the temperature in the data center at a certain level. So we're talking about lots of energy that is consumed here, and hence a lot of dollar cost, okay? But that's not the only motivation. The other motivation is that there are more and more government policies for building energy efficient or green ICT. So basically they have, certain percentage of carbon emissions that a particular data center provider can so they have quotas that they have to respect. And that's why basically Google and many other players are now building data centers in up north in the cold, in order, for example, to save energy. And there are all kinds of techniques to do that. Also using green energy sources such as solar and wind and whatnot. But the most important thing is to reduce carbon emission. And there are actually more and more policies, government policies in this respect, which also motivates, to reduce as much as possible energy consumption. So how do we reduce energy consumption? There are many different techniques out there in the literature. For example, at the level of a particular machine, using dynamic frequency scaling, speeding up or down, whatever the frequency of your CPU. And there are all kinds of techniques. But one important technique that operates at the level of an entire data center is called server consolidation. And the idea of server consolidation is basically to turn off the machines that are not used, and thereby saving energy. Why can we save energy in this case? Because if you take a machine that is idle, that is on and idle, which means executing nothing, it consumes up about 60 to 65% of the energy it would consume if it is used at its peak, utilization, if it was completely used. So if it is idle, it consumes about 65% of the energy it would use in its peak utilization. So we're talking about significant energy reduction, consumption reduction, if you basically turn off these unused machines. Okay, that's called server consolidation. So we wanted to look, before just going and trying to decide which machine to turn on or off, we wanted first to look at the data we have from Google to see if there is real potential in saving energy. All right? And we just basically looked at the CPU demand over the 30 days of the data we have, and the memory demand over the 30 days. And you can see here that there is significant fluctuation depending on the time of the day and the day of the week. Okay? Just by looking at this figure, or these graphs, we can see that there is potential to save about, just by looking at them, about 20% energy saving. Okay? So all right, so we based on this observation, or strong with this observation, we went on and we wanted to basically provision the capacity of the data center dynamically in order to support the workload. Okay, so vary basically the capacity or the number of machines that are turned on in the data center at any point in time in order to satisfy the workload at that particular time. Now, in order to do that, there are a number of factors that need to be taken into consideration. And one of them is heterogeneity of machines. Okay, that's what I've been claiming since the beginning of this talk. Okay, because it's very important to turn on or off the right type of machine, because if you turn on the wrong type of machine, you will not be able eventually to satisfy the workload. All right? The heterogeneity of task sizes and duration, very important, because that's, which machines to provision in the data center. The variability of task arrival rate. The workload performance requirement, for example, scheduling delay. This is very important because there is a trade-off, okay? If you want to be extreme, you're going to shut off the majority of the machines, and then if you do that, when you have workload that arrives, this workload will have to wait until you turn on the machine, boot the machine, configure the machine, and that will result in extended scheduling or queuing delay that can be unacceptable to a number of applications. So basically, turning off too many machines may have an adverse effect on some performance requirements, such as the scheduling delay. Also, the cost of capturing, of turning on and off servers, the so-called Tirwir effect. If you turn on and off a machine too frequently, too much, then the lifetime of these machines will go down. Okay, so the machine will die sooner than it should. Okay, so that's called the wear tear effect, and you want to minimize that. And finally, the fluctuating energy prices. I don't know about here in Tunisia, but for example in Canada, energy price or electricity price fluctuates over time. It's different from 1 hour to the other, for example, and this has to be also factored in because we're interested in minimizing energy cost, and obviously electricity price is significant in that respect. Okay. So, what is our solution approach? Our solution approach is first to classify tasks based on their sizes and duration using any clustering machine algorithm. And here we used a k-means clustering algorithm, very simple clustering algorithms, and we found that basically in the worst case, okay, it yields, you know, an error that is less than 5% in the worst case. So basically, we looked at the data, there are clear patterns, so easy to classify using very simple clustering algorithm, and that's what we found. Then we capture the runtime workload composition in terms of arrival rate for each task class, and then use a predictor in order to predict the arrival rate of each type of task. And here again, we used a very simple predictor. Specifically, we used the ARIMA model, and that showed very good results. Then we introduced the concept of container, okay? And we define a container as a logical collection of resources that is allocated to a task that belongs to a particular task class, okay? And then we use this container to reserve resources for each task class in the cluster, okay? So that's the main idea. So we use the task arrival rate to estimate the number of containers we need, and then we reserve these containers in the cluster. So this is the architecture of Harmony, the system that we built, okay, and deployed in a real cluster. So there are a number of modules involved. One of them is the monitoring module that collects statistics about the cluster usage, okay, and feed that into our system. So we have the task analysis module that basically captures the task arrival rate of each task class and analyze to determine that for each task class. Feed this information into the prediction module. The prediction module will predict the task arrival rate for each task class, okay? And then provide the information to the container manager. This is the most important component of Harmony. The container manager gonna use the predicted arrival rate of each task class as well as other information such as performance requirements of the application, notably the scheduling delay, for example, as well as other information such as fluctuating electricity price to do what? To determine the number of containers that we need to support the workload at the next time epoch, okay? The predicted arrival rate, all right? And then it provides this number of needed containers to the capacity provision module, which will turn on or off the appropriate number of machines in the cluster, as well as to the scheduler that will schedule the execution of the tasks in these containers in the cluster. Okay? So, I mentioned that the most important component is the container manager. And the function of this container manager is basically a dynamic optimization problem, okay? Or can be formulated as a dynamic optimization problem, all right? Now, we know that control theory is very good for solving dynamic optimization problems. So we formulate the problem as a control problem, the objective of which is to minimize energy consumption, okay, while in the same time satisfying performance requirement, typically the scheduling delay. So there are three terms in this objective function. There is the performance objective. It's which basically we try to maximize a utility that consists in minimizing the scheduling delay. So this is captured by the function f, which is a concave function, the exact shape of which is determined using queuing theory. And then we have the energy cost here, and the energy cost is the energy consumption multiplied by the electricity price at time t. And then we have the switching cost. This is the Tear-Wear effect, or the cost of switching on and off servers, okay? And the optimization is subject to two constraints. The first one is the machine state constraint that says that a machine is turned on only if it has at least one container, or it supports at least one container. And the capacity constraint, which basically states that all the containers or the virtual machines running on a particular server in terms of their resource utilization cannot exceed the capacity of this machine, as simple as that, all right? So, well, this optimal capacity provisioning problem is an NP-hard problem because it generalizes the vector bin packing problem, which is known to be NP-hard. So what we do is we come up with two heuristics. One we call CBS, and the other we call CBP. Okay? So in CBS, we statically allocate containers in physical machines using a variant of the first fit algorithm, whatever, that shows good performance. And then at runtime, we schedule the tasks into containers. So why we came up with two heuristics first? Because as you can see in this one, the container has to be aware, or the scheduler has to be aware of the container, the concept of container. So we came up with another one, which is called CBP. And here, instead of statically allocating containers into machines, okay, what we do is basically we just use the estimated number of containers needed to support the workload at the next time epoch in order to provision machines. And then use any existing or the existing scheduler in order to do the allocation of tasks into these machines. It can be first fit or whatever, what else, okay? All right. So let me tell you a little bit about the experiment, first with the experiment setup. So we classify tasks in each of the priority groups, okay? This here shows just the gratis priority group, and you can see that we found there are 12 distinct tasks in this priority group. So each bar here shows you the number of tasks in each task classes. And here basically we do the clustering using the k-means algorithm. So we see here the task size in terms of CPU and memory demand. And we can see here again that the confidence interval here the standard deviation is much less than the mean. So which kind of confirms the accuracy of the clustering here. All right. And here shows the clustering of the tasks in each of the task class based on task duration, okay, in the short or long, okay. And you see again here, so we use the clustering, the k-mean clustering algorithm with k equal to 2 here, and you can see here again that we are able to cluster the tasks very clearly into short and long tasks, and based on the observation that we made earlier, looking at the data traces. Okay, then we look at the the energy consumption model of the machines. Remember that in the Google cluster that we are working on, for which we have the data set, there are 10 types of machines. So this graph here shows only 4 of them. Okay, just for the clarity of the graph, we included 4 of them. And this shows the energy consumption model. So you see the blue line corresponds to an HP DL 585 C17 or whatnot, or G7, sorry. So that's basically so the graph here shows the energy consumption model based on the unit of CPU it provides. So this is the HP DL 585 is the largest size machine. It has 64 cores, okay, and the one that consumes less energy per unit of CPU provided, okay. And then comes after that the black one, okay, and then comes the green one, and then comes the red one. All right. So if you just, I know it's very hard to understand this curve. So basically, if you just project this curve, continue this curve, you see that basically it will surpass the blue one, okay, for the same amount of CPU unit supported. All right. So the blue is the best type of machine, has the highest capacity with the lowest possible consumption, energy consumption. So just by looking at that, one intuitive solution would be, or intuitive idea to minimize energy consumption would be to say, why don't we provision, basically turn on the most energy efficient machines first, okay, in the cluster. So, or basically turn on machines based on their decreasing energy consumption in the cluster. So which means that turning on the blue machines first until we have no more blue machines, then turning on the black ones and then the green ones and the red ones. And this way, okay, intuitively we will reduce energy consumption, okay? And that's basically what we did and implemented that as a baseline algorithm to which we're gonna compare CBS and CBP, all right? So this shows the aggregate task arrival rate, okay, based on the traces, and this is the number of required container using the predictor based on this arrival rate, so we know how many containers we need to support this workload. So this is for the experiment setup. Let me show you the experiment results. All right, so this here shows the results, okay, in terms of number of machines active in the cluster to support the workload that we have seen in the previous slide. Okay, and this is using the baseline turning on the most energy efficient machines first. And obviously you can see that the baseline algorithm turns on the blue machines first, then the black ones, then the green ones, then the red ones. All right, and this shows the performance in terms of number of machines active in the cluster to support the workload using CBS and CBP. Okay, and you can see that obviously here this will reduce the number of active machines to support the same workload quite significantly compared to the baseline. See the number of machines, 8,000 in the case of the baseline, about 1,500 here in the case of CBS and CBP. And looking at that from a different perspective in terms of the energy consumption, so we see that CBS and CBP reduce the energy consumption by 28 and 14% respectively compared to the baseline. And the baseline, okay, is already kind of improves in terms of energy consumption compared to not taking into account the consumption model of machines. Okay, so why is it significant? Why 14 and 28% is significant? Actually, 3% improvement in terms of energy consumption in a Google cluster translates into over $1 million cost saving. Okay, 3%. Over $1 million. So we're talking about significant cost saving to a big cloud provider like Google. Obviously, as I mentioned, there is a trade-off between energy consumption and scheduling delay. So we also measured scheduling delay for the baseline and for CBP and for CBS. So we can see that CBP outperforms the baseline in terms of scheduling delay, and CBS outperforms both the baseline as well as CBP. The main reason CBP does better than CBS is because there is a very better coordination between the scheduler and the containers. Okay, because remember the scheduler has to be aware of the concept of containers. Now the downside of that you have to modify the scheduler in order to do so. Okay, but obviously it provides better results. I don't know how am I doing in terms of time? I didn't pay attention to the time I started. Anyway, I can conclude. So I think cloud computing is I think the reason I was mentioned at the opening ceremony here. It's a very important concept for computing and as well as for networking and for already and for the foreseeable future. I think the message that I wanted to convey during this talk is the issue of heterogeneity that, as I mentioned before, has been largely overlooked and definitely has well, if you want to do research that has a impact in reality or in practice, I think you cannot ignore this very fact. And now the main reason, that most of the papers published in the literature do not take this into consideration because they are, first of all, complicated. It makes like the modeling or for those papers that are more analytical in nature, it becomes a little bit complicated to avoid simplifying assumptions. For example, the uniformity of workload or the uniformity of the machines in the cloud. But the other reason is the fact that there is no data available for people to use, right? And I hope that this problem is now solved because remember all the data I showed you before. We made it available. Actually, you can access it from this link here. It is available. Not only the raw data is available now, but also the processed data. Okay, so we spent several months processing this data, okay, and we made this data available so you can save yourself a few months of extra work and you can readily use this data, for example, to evaluate your your algorithms or proposed ideas. I hope that I also pointed out some interesting research issues or questions that are still looking for solutions. So if you're interested, I hope that you can contribute to that and obviously use the data to make these more, even more impactful. Let me, before I finish, let me acknowledge some of my collaborators. Chi Sang finished his PhD in September. Mohammed Faten Zani, I think some of you know him. He, I think, started at NC and did his PhD in Montreal and has been doing postdoc at Waterloo with me for the last 2 years. Lu Chang worked with me at some point. She's been out in the working for the industry for a while. Chu Zhang, as a visiting researcher from China, was there only for a little amount of time. And finally, Joe Hellerstein from Google, and he basically contributed lots of money and most importantly the data that we used to for this work. So okay, and yeah, time for questions. Même en français.
C'est pour ça
qu'on peut faire les questions en français.
S'il y a des questions, il y aura sûrement. Je vous remercie pour la présentation, pour les idées, pour les différents thèmes abordés. Il y a sûrement une question. C'est bon.
Bon, merci bien pour la présentation. Mais j'ai une question par rapport à l'architecture valable pour qu'on puisse faire ces optimisations des énergies, des charges, ainsi de suite. Est-ce qu'une question pour les opérateurs télécoms, là où on dispose d'une architecture surtout physiquement dispatchée sur une zone assez vaste et surtout variée, donc les machines, peut-être bien les terminaux qui servent à l'accès, ainsi de suite. Est-ce qu'on peut, par exemple, appliquer ce type d'optimisation sur toute l'énergie pour les opérateurs? Merci bien.
Ok, je vais essayer de répéter votre question pour être sûr que j'ai bien fait ça. Donc, vous parlez d'un opérateur, ça peut être un opérateur, vous avez parlé d'opérateur télécom, mais ça peut être un provider de cloud. Hein. C'est quelqu'un qui a une vaste zone, qui peut couvrir ça avec une infrastructure comme ça. Et donc, ça veut dire qu'il y a plusieurs data centers, c'est ça, par exemple?
C'est pas forcément un data center, parce que ça va dépendre de l'architecture.
Mais là, on parle surtout de cloud, ok? Donc, si il n'y a pas de data center, il n'y a pas de cloud. Ok, donc le data center, c'est l'unité d'infrastructure d'un cloud. Maintenant, on peut parler de plusieurs data centers, des core data centers, des grands data centers, mais on peut aussi parler de ce qui est un peu en train de se mettre en place, et surtout dans le cadre des opérateurs télécoms, ce qu'on appelle les clouds, les multi-tier clouds. On a des clouds, des edge clouds, des petits data centers qui sont au edge, c'est-à-dire proche un peu des utilisateurs. Et donc après des core data centers qui sont dans des endroits éloignés. Comme j'ai mentionné tout à l'heure, les data centers en général sont déployés dans des endroits éloignés où il y a à proximité une source d'énergie importante, et puis c'est pas coûteux de déployer là-bas, ou ça peut mettre au pôle Nord par exemple pour réduire la consommation d'énergie à cause de la température, peu importe. Donc quand on a plusieurs data centers, oui, on peut faire par exemple, on peut faire de l'optimisation d'énergie par exemple en plaçant les services dans les data centers dépendamment de l'utilisation, dépendamment du prix de l'électricité. Par exemple, si vous prenez Google, il a des data centers un peu partout. D'accord? Et un peu partout dans le monde. Et donc par exemple, une façon d'optimiser, ce serait de suivre par exemple le prix de l'électricité. Okay, par exemple, la nuit, le prix de l'électricité, à partir d'une certaine heure de la nuit, il descend. Et dans certaines parties de la journée, il peut être augmenté. Donc, tu peux finalement, quand tu as le workload qui arrive, tu peux le placer dans les data centers de façon, par exemple, à minimiser ta facture d'électricité. Par exemple, là où l'électricité est la moins chère, eh ben, je vais exécuter. Bon, donc Google, en général, il ne fournit pas les ressources à des utilisateurs externes, mais à ses propres utilisateurs, par exemple pour implémenter le Google Search, etc. Donc, il peut facilement router le workload dans les data centers, considérant le prix de l'électricité. En même temps, avec d'autres contraintes d'optimisation, que par exemple le temps de réponse. On ne va pas mettre la requête d'un utilisateur ici, à l'autre bout du monde, si ça ne respecte pas la latence de bout en bout. Donc il y a plusieurs contraintes qu'on peut prendre en considération, mais en même temps, utiliser donc cette infrastructure distribuée, ces différents data centers, pour optimiser l'énergie. Mais il y a plusieurs autres exemples auxquels on peut penser aussi.
Une autre question?
Oui.
Tout d'abord, je vous remercie pour cette présentation donc, qui s'inscrit dans le cadre d'un domaine de recherche en plein essor qui est le cloud et le big data. J'ai juste une petite question concernant, parce que là vous avez parlé du processing et là il y a le storing. Parce que par exemple Hadoop c'est MapReduce plus HBase, donc pour le stockage des données. Ma question c'est que, parce qu'à un moment donné vous avez présenté, donc vous avez dit donc l'hétérogénéité de la plateforme, des machines virtuelles ainsi que du workload peuvent affecter ou doivent être considérées dans le modèle du scheduling. Est-ce que l'hétérogénéité des données, data, parce qu'on parle data, donc ça peut être structuré, non structuré, est-ce que vous pensez que cela peut affecter ou doit être considéré comme des métriques dans le modèle de scheduling? Voilà. Et peut-être une deuxième question, donc, parce que là on parle de server consolidation, donc on peut donc éteindre des serveurs, mais en fait, bon, on sait bien que les données doivent être proches du processing pour éviter le temps de latence. Est-ce que le fait qu'on est en train de migrer d'un serveur à un autre, ça peut pas affecter en fait ou ça va augmenter le temps de latence si jamais les données ne sont pas bien distribuées dans le serveur? Et je vous remercie.
Oui, en effet, c'est des questions toutes valables. Oui, absolument, il faut prendre ça en considération. Donc si on parlait vous parliez de Hadoop, ce que fait par exemple le scheduler, qu'est-ce qu'il fait? Il va d'abord aller chercher les données. Ensuite, il va essayer de placer les map tasks et les reduce tasks sur les machines où il y a les données, de préférence, s'il y a des slots disponibles. S'il n'y a pas de slot disponible, à ce moment-là, il va se résoudre à les placer éventuellement sur d'autres machines, quitte à aller chercher les données, parce qu'à la fin de la journée, il accède aux données, quitte à aller chercher les données à partir de machines distantes. Et donc là, il y a une implication au niveau de ce qu'on appelle le I/O, etc. Et c'est pour ça que c'est un grand problème dans les data centers, parce qu'il y a énormément de trafic, et donc ça nous emmène aussi à des considérations de type réseau, quel type de réseau, quel type d'infrastructure de communication à l'intérieur du data center pour supporter un peu tout ce trafic entre les processus qui s'exécutent et les données qu'ils cherchent. En effet, au niveau de la migration, c'est pareil. Donc migrer un processus éventuellement pour l'éloigner des données. C'est pour ça que quand on fait de la migration, c'est quand on regarde un peu la littérature, quelque chose qui est très très négligé dans la plupart des papiers, c'est que on peut regarder un peu les avantages de la migration, aller éviter un hotspot réseau, ou bien par exemple aller dans un serveur qui est moins chargé, ou faire de la consolidation pour sauver de l'énergie. Mais il y a un coût à la migration, et ce coût là, et c'est le coût par exemple, pas seulement le coût éventuellement de déplacer le processus loin des données qu'il accède, mais aussi le coût de déplacer l'image de processus sur le réseau qui peut conduire à des congestions, puisque la migration, si elle est utilisée de façon extensive, et ça l'est aujourd'hui pour différentes raisons, qu'on peut imaginer qu'il y a énormément de migrations dans tous les sens qui ont lieu, et ça a un coût, et ce coût est négligé. Donc il faut considérer le coût, notamment l'accès à distance des données. Maintenant, on peut aussi imaginer que les données peuvent être répliquées, etc., etc. Donc, on peut, par exemple, dans le cadre du scheduling, on peut faire du prefetching, okay? Donc de façon anticiper donc le besoin de certaines données, donc aller les chercher de préférence. Dans le cas de la migration, on peut imaginer que les données sont redondantes, mais si ce n'est pas le cas, ça devrait être considéré comme un coût dans le cadre de l'optimisation, et puis évaluer est-ce que c'est une bonne idée de migrer ou pas. Et puis aussi migrer quelle machine, et je sais pas, on vient juste de faire de soumettre un papier qui consiste un petit peu à organiser un peu un échéancier, un planning des migrations pour arriver à optimiser de façon meilleure.
Bien, merci Raouf pour cet excellent exposé, et ça fait plaisir de te revoir ici parmi nous en Tunisie.
Plaisir partagé.
Je voudrais revenir sur l'étude a focalisé beaucoup sur les données que tu as pu obtenir de Google. Par rapport aux autres grands clouds comme avec Facebook ou bien Amazon, je dirais, j'ai l'impression que si on prend Google, Facebook, tout ça, il y a des patterns d'application peut-être assez identifiables à la limite. On pourrait peut-être faire des prévisions sur le type de pattern d'application et de trafic. Par contre, si on va dans d'autres sites où on a plus d'infrastructures as a service et tout ça, peut-être là, la différenciation ou bien la diversité va être beaucoup plus importante. Je vais juste avoir ton opinion sur ça d'abord. Et puis j'aurai une question sur les résultats à la fin ou par rapport au baseline ou l'optimisation, parce que là, si j'ai bien compris la courbe de...
C'est là ou l'autre?
Oui, le baseline, c'est toutes les machines sont... Il n'y a pas de restriction, il n'y a pas de consolidation. Non, si, cette
celle-là,
oui.
C'est le scheduling, ça c'est le scheduling delay.
Scheduling. La première courbe en haut à gauche, c'est là où il n'y a pas de... Toutes les machines sont disponibles tout le temps, c'est ça? Le baseline.
Ça c'est plutôt le scheduling delay. Les machines, c'est là, en fait.
Oui, je veux dire, dans le scheduling delay pour le baseline, vous supposez que toutes les machines sont on all the time ou all the machines?
Non, c'est un peu le temps que ça prend pour scheduler quand le workload arrive, le temps que ça prend pour que les jobs sont schedulés. Non, ils sont pas vous voulez dire, est-ce que les machines sont mises sont turned on dans un ordre précis, dépendamment de la prédiction du workload. Elles sont pas toutes, je suppose pas qu'elles sont toutes on, évidemment. Oui, non, si tu veux, le baseline, il fait une certaine optimisation. Hein. Le baseline, qu'est-ce qu'il fait? Donc, dépendamment du workload qui arrive, qu'est-ce qu'il va faire? Il va allumer les machines, commencer les machines, mais il va le faire dans un certain ordre. Des machines les plus performantes, d'un point de vue consommation d'énergie, aux machines les moins performantes. Par contre, la différence... Donc, il y a déjà une optimisation par le baseline. Donc, la différence qui fait que CBP et CBS font mieux que le baseline, c'est le fait qu'ils prennent en compte l'hétérogénéité, le type de workload et le type de machine à mettre en place. C'est la seule différence. Et ils sont capables de faire mieux que le baseline parce qu'ils font ça. Alors, le problème avec le baseline, c'est que parfois, par exemple, il va commencer par mettre les machines bleues, la HP 500, DL 585, il va les allumer en premier parce qu'elles sont les plus performantes. Mais c'est des grosses machines aussi. C'est les plus grosses, c'est celles qui ont 64 corps. Et alors ces machines-là, parce qu'elles sont allumées en premier, elles vont être aussi affectées à des petites tâches. Du coup, il va arriver un moment où il y a des grandes tâches qui arrivent et qui ne peuvent pas être schedulées sur ces grandes machines et non plus sur les machines qui restent parce qu'elles n'ont pas la capacité suffisante. Et donc, c'est ce qui fait que donc il y a un scheduling delay qui peut être plus important dans le cadre du baseline comparé à CBS et CBP qui font un meilleur matching entre le type de workload, les types de tâches, etc. et les types de machines qu'on a dans le cluster. Mais sinon, à la base, le baseline est aussi... et on a comparé, en fait, si on aurait comparé à une situation où toutes les machines sont on, bien sûr, là, le gain serait encore beaucoup plus important. Mais c'est vrai qu'au niveau scheduling, là, je vois encore un peu plus ton point. Au niveau scheduling, si on a toutes les machines qui sont allumées, normalement, le scheduling serait minimisé, serait plus petit. Et donc, c'est contre-intuitif. Pour revenir à ta première question, qui est une bonne observation, au niveau de, si on regarde par exemple des infrastructures as a service comme Amazon, comparé à des private cloud comme les Google, etc., est-ce qu'il y a une différence? Est-ce que les données seraient différentes? On n'a pas de données sur Amazon. Mais une des raisons pour laquelle je penserais que finalement il n'y aurait pas une énorme différence, c'est le fait que même connaissant le cas Google, par exemple, Google est utilisé aussi comme infrastructure as a service, mais pour des clients Google. En fait, l'infrastructure est fournie à différents groupes dans Google qui vont faire à peu près comme un utilisateur lambda va faire au niveau de Amazon, va demander des instances X, Y, Z pour exécuter quelque chose. À l'intérieur de Google, ça marche aussi comme ça. Ils ont, c'est-à-dire les gens qui ont besoin de capacité de calcul et de stockage, eh ben, ils vont aller donc demander de l'infrastructure comme un service à l'intérieur de Google. Ça suggère qu'éventuellement, Maintenant, il est vrai que peut-être l'utilisation à l'intérieur de Google a un certain pattern qui peut être différent des utilisateurs lambda. C'est très possible. On n'a pas de données sur Amazon, mais qui pour dire de façon définitive est-ce que ça pourrait être différent ou pas. Ceci dit, même si on regarde Amazon, par exemple, on a travaillé sur Amazon dans le cadre des spot instances, les trucs où, par exemple, le prix est déterminé selon le marché, market-based auction pour déterminer le prix. Et là, on voit, par exemple, qu'il y a des patterns assez clairs, par exemple, au niveau, parce que en regardant rien que le prix des instances, qui dépendamment de l'offre et la demande. Et on voit que, par exemple, parce que là, par exemple, si tu vois Amazon, sur le site de Amazon, tu trouves le prix des VM instances, des machines virtuelles, à Amazon, surtout sur des grandes périodes, sur différentes régions, parce que c'est divisé en zones, Amazon, les clusters. Et tu trouves le prix de toutes les instances sur de longues périodes, des mois et des années. Et tu vois finalement qu'il y a aussi là-bas un pattern assez clair qui reflète finalement la demande. Parce que le prix dépend de l'offre et la demande, et donc il y a clairement un pattern là-bas aussi. Mais est-ce que, par exemple, les datas qu'on a ici s'appliquent de façon identique à Amazon? Ça c'est pas, je ne suis pas sûr.
Merci.
Une toute dernière question.
Non, mais allez-y, hein, ne vous limitez pas.
Merci, Arish. En fait, j'ai 5 questions.
Vous en avez 5?
5, oui.
On peut prendre un café.
En fait, la première, c'est que je voudrais savoir si les tasks, les jobs, ils sont divisés en plusieurs tasks. Et les tasks là sont-ils dépendants ou indépendants lorsque vous faites le scheduling?
Oui, un job est composé d'une ou de plusieurs tâches.
Oui.
Ok. Donc, et comme on a vu dans les données, la majorité des jobs sont petits du point de vue nombre de tâches. On a vu que par exemple 50% des tâches dans Hadoop à Facebook ont 2 tâches map seulement, et que 1% des jobs peuvent avoir plusieurs milliers de tâches. Okay. En général, quand on parle de jobs de type MapReduce, les tâches sont indépendantes. Les map tasks sont indépendantes. Les reduce tasks sont indépendantes. Mais les map et les reduce tasks ne sont pas indépendantes parce que les reduce utilisent le output des maps pour faire leur... Donc il y a une dépendance là-bas. Et en fait, le modèle a l'air d'être simplifié. Ici, on a les maps et les tasks, mais il y a aussi d'autres phases. Il y a ce qu'on appelle les shuffles, les sorts, etc., qui sont entre le map et le task. Donc, il y a une certaine dépendance dans le processus jusqu'à l'aboutissement du résultat. Et cette dépendance, d'ailleurs, peut conduire, si par exemple une tâche de type map Et retardée, elle peut avoir un impact sur l'exécution du job complet, ce qu'on appelle le problème des straggler tasks. S'il y a une tâche qui est en retard, elle peut retarder le job en entier. Okay? Et c'est pour ça, par exemple, Hadoop, il a une technique qui, on mesure le progrès d'exécution d'une tâche, et si on se rend compte qu'une tâche peut être en retard, qu'est-ce qu'on fait? De façon proactive, on va relancer l'exécution de cette même tâche sur une machine différente pour éventuellement éviter le problème de ce qu'on appelle les straggler tasks. Une longue réponse pour une question très, très simple, désolé, mais allez-y. Deuxième.
En fait, you said that you are going to classify tasks into clusters according to the execution time. How you estimated the execution time?
How do we estimate the execution time of tasks? Well, so typically map tasks are run multiple times in the cluster. So we basically, the same tasks are executed, the same jobs are executed often, right? But then there are different techniques. So Hadoop tells you the progress of the task. So you know how the progress, and the progress of the task is based on how much data has been fetched. We're talking about data because typically they process data. So basically by analyzing how much data has been already accessed, you know the progress of the execution of the task. Then we take a sample execution time, say 30 seconds, and divide that by the progress, the task execution progress, which is typically provided by the task. Basically you have the task tracker. There is a task tracker and there is the job tracker, and the task tracker basically follows the execution of the task and then sends heartbeats to the job tracker or the job scheduler, and so that's how we know. So we can determine this.
There is a learning paradigm behind that.
Excuse me?
A learning paradigm, somehow learning.
Learning,
yes.
Yeah. Actually, no. You can do that basically in real time. You know the progress of the task execution in real time.
The container, its function is to provision machines according to the capacity and the cost.
Is there a particular slide?
Yes. You presented the function to optimize is the cost and the capacity, and there is constraint.
The optimization function.
Yes.
Here.
Yes, that one. The objective function, in fact, what I know is that the objective function will, its output is just one optimized point. And as we know, the scheduling is an NP-complete problem. So you have...
No, scheduling is not an NP-complete problem, but that formulation is NP-complete.
So here how you are going to find a compromise solution that will give you the best fit for these three functions. How you did that?
I'm not sure I understand your question. So basically here, we turn everything, you want basically to maximize this, right?
Yes.
And this is as a sum, right? So you have so everything is turned into dollars. Basically, everything is basically the same unit across, and then basically you have the performance objective minus the. We turn it into utility, and we try to maximize the utility, okay? And the utility is the difference between the performance improvement and the energy cost, right? And everything is turned into a dollar. I can tell you more about the details, or I can direct you to the paper, but so basically you try to maximize this sum. Yes. That's what you can do. But what is your question exactly?
In fact, I will...
Which is typical objective function.
The subject to constraint, yes. There are two constraints.
You're talking about the constraints.
Okay, yes. For the constraint, is there some suitability function that you could with that best achieve the satisfaction to this constraint?
Well, it's if you so again, I think you have to think of it from so again, this is a linear program, and NP hard to solve, and that's why we come up with a heuristic. And the idea of the heuristic is, I think I explained before. Yeah, so the heuristics consist basically to allocate. Is that your question? I'm not sure. Which constraint? I'm not sure I'm following your question here.
For the constraint, you have two constraints.
We have two constraints.
How you know that you satisfied both two constraints? That's in a good way, in the best way.
Well, we don't necessarily need to satisfy them in the best way. We need them to be satisfied. That's basically what we do. We don't go any further than that. We just make sure that none of this constraint is dissatisfied at any point in time. So during the optimization, yeah. We have to make sure that no machine is, but then are they satisfied in the best possible way? That's a different story. We don't look into that. At least here, yeah.
Of course, I want to ask about.
No, feel comfortable. Don't worry about that.
The virtual machine are changing dynamically in the time. Virtual machine. Yes. In fact, how the container get the updated data about the state of virtual machine, because if I understand right, the container provision tasks to machines. That's correct.
No. You can think of the container as a logical concept. Okay, it's just a logical amount of resource that we reserve in a particular machine. Okay, the virtual machine is what is scheduled later on that particular reservation. Okay, so it's just a logical thing. Now the virtual machine is like, you can think of it as almost a physical thing, right? But the container is just say, okay, how much resources do we need for the workload? And what we do is we classify the first of workload into different classes of tasks, and then and each task of class will need a different size of containers. Okay, and so we have the workload, we classify the workload. Okay, predict how much of such workload gonna arrive, and then reserve as many resources as we need for these different pieces of different types of workload. And that's just, we reserve the resources, okay? So, and then after that, there are two techniques. Like in one, basically we have to, the scheduler has to allocate the tasks in the corresponding reservations. Okay, but here the scheduler has to know which container has been reserved for which type of resource. Okay, the container again is just an amount of resources. Okay, it's not a physical concept. In the second case, we just basically provision enough machines to support all the containers we need. And then we use any scheduler. And obviously here the scheduler can mess up, basically assign the wrong tasks to the wrong machines. Okay, while in the first case, the scheduling gonna be really precise, where the particular type of task will be allocated to the machine that supports the container or the reservation of resources that was made for that particular task.
Thank you.
You're welcome.